transform of this, yeah? Okay, so if you were to plot this, this looks like a parabola, yeah? So this is an even function, somewhat.
Yeah.
Okay, and let's say that this is minus pi. Well, it is an even function, not somewhat. It's an even function. So from minus pi to pi, and if you were to do many of them, you'll get, parabola-looking shapes like this.
Yeah.
From minus pi to pi. So this is an even function. Okay. Now, you tried to break this into. You were saying that you tried to break this into cosine hyperbolic, right?
Yeah.
You were saying this is equal to e to the x plus e to the. First, let's since it's an even function, we can immediately say that. So for the Fourier transform, b's of n are all equal 0. Okay, so we have to worry about the a's of n. Okay, the a's of n is 2 over L integral from 0 to L, with L being pi in this case. So we integrate from 0 to pi and we double it, we multiply by 2, rather than going all the way. F of x cosine n pi x over L. Cosine n pi x over L. Okay, dx. Now, the way you did it is you rewrote cosine hyperbolic as e to the x plus e to the minus x over 2.
Yeah.
But that just makes the problem longer. Let me tell you why. Because the second you multiply this by cosine n pi x over L, you've got two integration by parts, and they both have to repeat, and you get yourself into two long integration by parts. Because then you have e to the x cosine n pi x over L, and then you have e to the minus x cosine n pi x over L. Yeah. So you would rather integrate this as cosine hyperbolic, not as exponential.
So how would
equivalent.
How would that be integrated then?
By parts. So you would say, okay, so you would say then we'll go after the ANs. So AN will be 2 over pi, okay, from 0 to pi. F of x is cosine hyperbolic x times cosine n pi x over pi. So you're going to get cosine nx, because the pi will cancel out, dx. Okay? And we're going to do an integration by parts on this one.
Yeah. Wait, where did you say a pi cancel that?
You have, oops, wait, this is an x, not a pi. Here, n pi x over L.
Yeah, I know L is pi, so that, yeah.
Yeah, so L is pi.
Yeah, I got that.
Okay, so here you have two integration by parts, and you'll be done. So this needs by parts, yeah. So you know how to do by parts?
Yeah, I'm not sure how I would do it.
So by parts meaning the integral of u dv equals uv minus the integral of v du. That's the by parts.
Yeah.
Yeah, so you could call cosine hyperbolic your u.
So what would be? Oh yeah. So then the derivative of that. Yeah.
So u is cosine hyperbolic x, which would make your du sine hyperbolic. And you would make
Would it be negative?
no, There's no negatives in the hyperbolics.
Alright.
It's always positive. And maybe it was a better
Oh, yeah, it is.
idea to call the other one u, so we don't have to divide by n.
No, but then the other one,
Uh,
because then it would start repeating though. The other
yeah, regardless, they'll both repeat. Doesn't matter. So maybe a better strategy is maybe to call u to be cosine nx, which would make du minus sine nx times n. So minus n sine nx. And then dv would just be cosine hyperbolic, which would make v sine hyperbolic. Okay?
Yeah.
So then your integral becomes so we have cosine hyperbolic x, cosine nx. We will integrate and then at the end we will evaluate. So that's uv. So that's cosine nx sine hyperbolic x minus the integral of v du, which will be plus n um, v du. So that's sine sine hyperbolic x times sine nx. From 0 to, we'll evaluate at the end. So now we get ourselves into another integration by parts, which is this. Okay, so here we have u so here we will do another integration by parts. So u is sine nx um, and um, let's move it here. U is sine nx, which would make du n cosine nx, chain rule, and then dv is just sine hyperbolic x, which would make v cosine hyperbolic x. There's a dx here, and there's a dx here. Okay, and now we plug in again, so we get the integral of cosine hyperbolic x cosine nx equals cosine nx sine hyperbolic x plus n, open gate here, and we'll do by parts here. So uv, so that's sine nx times cosine hyperbolic x minus the integral of v du. So v du will be minus n, so we can put the n here. V du will be cosine hyperbolic cosine nx. you can see that it repeats.
Yeah.
So now we can move it to the left. So this becomes um, cosine nx sine hyperbolic x. So there's only one integration part to do. Versus the exponentials, you'd have to do this twice. Sine nx cosine hyperbolic x minus n squared cosine hyperbolic x cosine nx dx. And this is equal to cosine hyperbolic x cosine nx dx. And now okay, and now you could see that I could move this backwards to the left, and this is the same thing as this guy. So we would get 1 plus n squared times the integral of cosine hyperbolic x cosine nx equals these two here, cosine nx. So I took the cosine hyperbolic x cosine nx integral dx common factor, cosine nx sine hyperbolic x plus n sine nx cosine hyperbolic x. Okay, and now I could just divide by 1 plus n squared, and you'll be done. So the integral of cosine hyperbolic x cosine nx is equal to 1 over n squared plus 1 times this. Sine hyperbolic x plus n sine nx cosine hyperbolic x. And we can evaluate all this. Now we can go back to the bounds. So the bounds were 0 and pi, and there's 2 over pi before it, right? So there's here 2 over pi, and this is going from 0 to pi, so we'd have to evaluate this from 0 to pi. So then this becomes 2 over pi times n squared plus 1. Okay, so if we plug in pi, we get uh, um, we get 0, so we plug in pi, so we get cosine pi x sine hyperbolic pi x, pi I mean, plus pi sine pi x or pi n, which will be 0, cosine hyperbolic pi. So this whole term will be 0 because all the multiples of pi, their sign is 0. So that's the first guy. Minus, now we'll put in the zeros. So cosine 0 is 1, yeah? So we will get sine hyperbolic 0. Sine hyperbolic 0
This is 1. Oh, no, it's negative 1. It's 0.
is 0.
No, it's 2. Sine hyperbolic 0 is 2. Because e to the 0 plus e to
Sine
the
hyperbolic 0 is 0. No, that's minus. It's e to the x minus e to the minus x.
Oh,
So 0,
no, that's cosine.
and then
Isn't it
cosine hyperbolic is
Isn't it?
1.
It'd be 2.
No, because you divide by 2.
Oh, right.
So, but then the sign term is 0, so that whole thing is
Right.
knocked out. Okay, so we did in fact get somewhat of a clean expression here. Cosine and pi. Cosine and pi. Sine hyperbolic pi. No? Okay, so at the end of the day, we get a of n to be 2 over pi times n squared plus 1 cosine n pi sine hyperbolic pi. Okay, so that's our coefficient right there. Understand? So we can figure out the first few coefficients. We can go after a0 now. So that's 2 over pi. Cosine pi is minus, cosine 0 is 1. Sine hyperbolic pi. So that's our a0. Yeah? And what's our b1 or a1? Is 2 over 2, so that becomes 1 over pi. If n is 1, you get times minus sine hyperbolic pi. And a2 is 2 over 5 pi. Now sine 2 pi will be positive now. So this will be an alternating expansion because of the cosine of pi. Sine hyperbolic pi. So it looks from this analysis, well, we know that cosine n pi will either be a plus 1 if n is even, or will be a minus 1 if n is odd. Okay. So we could rewrite this as um, um, a's of n. If I were to keep on going here, I could rewrite this as 2 over pi, the summation of -1 to the n, because cosine n pi is nothing but that, right? Times 1 over n squared plus 1 sine hyperbolic pi is a constant. I can put it out. So 2 sine hyperbolic pi over pi. Now at 0 we get 1, so we get 2. Yeah, it works at 0 too. So we can get the series started from 0 to infinity. No?
Alright, so how did you end up integrating this stuff?
And as such, our Fourier transform will be what?
How did you end up integrating this?
Hmm?
How did you end up integrating this?
By parts. So this is our a's of n here.
So when you did,
Right.
but it repeats when you do by parts. Where do you cut off? Like where do you stop?
So now, so what would the, yeah, I'll show you in a second. So now, what would the Fourier transform look like? Right? This expansion.
Yes.
So 1/2 a0 plus, all the bn's are 0, so we don't have to worry about this. A1 cosine x plus a2. And those a's, we can get them from a's of n, right? Just like we did. A2 cosine 2x plus a3 cosine 3x plus dot 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 plus dot dot dot. Okay, what was your question?
How do you know when to stop when it's because it repeats?
Yeah, I showed you like yesterday.